point. There we are. Okay, welcome back. Welcome to March. We're now over halfway through the course, at least in terms of if you count the lectures. We're halfway through the course. Today we're looking at section 3.3 of Tau. Tau's coverage of this is pretty good. So if you've stopped looking at the book, you're welcome to go back and look at it again. We're looking at what we can do with uniform convergence. So we're going to have two results today. The first one is just straight out of last semester, but we're going to state it in the more general language. The proof really doesn't change. Okay, so this will essentially be a proof we gave last semester, but it's good to see the proof another time, and maybe it'll seem easier this time. Okay. So, without further ado, our first result, we will call it a theorem. We're going to need some metric spaces. And now we're going to take a sequence of functions a sequence of functions that are all continuous at a point. And we're going to say if they converge uniformly, then their limit is also continuous there. So a bunch of functions, they're all continuous at a point, they converge uniformly. To some function f. Okay, just remember that in the last lecture, when we looked at pointwise and uniform convergence, we saw that this doesn't have to happen for pointwise convergence. In some sense, this is precisely why we have this notion of uniform convergence. Okay, are there any questions about this statement? Okay. Let's prove it then. So this proof, lots of people call this a 3 epsilon argument, because there are going to be kind of 3 things that are epsilons. I'm going to make them epsilon over 3, so we end up with an epsilon. But let epsilon be arbitrary. Epsilon is going to be when we say f is also continuous at A, that means for any epsilon there exists a delta, so that if we're within delta of the point A, then our function value is within epsilon. Okay, that's going to be our epsilon. Okay, now our sequence is converging uniformly, so at some point we're going to be within, say, epsilon over 3 of f. So that is the first thing we'll do. So I'm just using uniform convergence, just the definition of it, but I'm going to insist on epsilon over 3 instead of epsilon. Okay. I highlighted the part that we're getting from uniform convergence. This is true at all, this value of n works for all x in x. That's pretty important. Okay. Now, it turns out we don't actually care about about most of those. We just care about f sub capital N now. So we're actually just going to focus on that one. So that function is continuous at the point A. Okay. So because that one is continuous at A, we have some delta so that if a point is within delta of A, then the distance of the function values of the function f sub capital N between that and A will be less than epsilon over 3. So let me just write that down. This is just the definition of continuity. Okay. Any questions so far?
So at this point, we're saying we have if x is close to A, then the fn of x is close to fn of A, and then that is showing the fn, and then we have fn is close to fs.
Mm-hmm.
That's what you're writing right now.
Yeah.
So I guess I'll just find out in a second. I don't really see where the missing link is or where the uniform convergence is really necessary yet.
Oh, okay. Well, we'll get to that in a second. We might have to come back to talk about that. But the point where we're at is that, as I said at the top here, Fn and F are close everywhere. And then Fn of x and Fn of a are close. And I guess I should say here, when a is close to, when x is close to a. Okay. And now we're going to triangle inequality this. Therefore, when we have this, okay, then let us look at the distance in y, in the codomain, between fx and fa. Okay, that's what we want to show is less than epsilon. If we can show that's less than epsilon, then we've proved continuity at a. Okay? Well, we're going to triangle inequality this thing. So we are going to go, remember, so I think the way to think about the triangle inequality is you're going from, say, fx to f of a, and you just add some point in between. And now we'll just go via that point, and our distance can't be lower. Okay, so let's go from f of x, let's go to fn of x. And then from fn of x, let's go to f of a. Okay. Are any of these small yet?
The first one is.
Yeah, the first one is small, so we're happy there. The second is not, so we have to do another triangle inequality there. We want to compare fn of x to fn of a. So I'll keep the first term. And now we're going to go to fn of a, and then from fn of a to f of a. Okay, and then we're going to conclude that it's less than epsilon. Let's just double check why. The first one, the first quantity and the last quantity are both small because we're getting this uniform convergence. So those are both small because of that. The one in the middle is small because of the continuity of f sub capital N. Okay, it's three quantities, all less than epsilon over 3, so they add up to less than epsilon.
So just a quick question. So you really only need uniform convergence restricted to the domain of this like delta ball around A?
Yeah. Yeah, that's a good question. That's a good point. We only need the uniform convergence in a neighborhood of A to conclude this. We don't need uniform convergence everywhere in X. That's the standard kind of restrict the domain thing. So it's a good note. If we have uniform convergence in, say, a ball of radius r centered at A, let's just restrict our domain to that. So we'd end up considering the metric space. I'm just going to write this because it amuses me. We would have the set, which is the ball of radius r centered at A, and then the metric from X restricted to the Cartesian product of two copies of that ball. Okay.
I have another question / comment.
Okay.
So is this similar, so using this, like for every, for all the, we only require balls for this to work? Is it similar to how, like, for the real numbers, the whole set isn't compact, but every like closed set is compact, and that gives us completeness? Can we say that we're uniformly convergent on all of the balls, which then says that the function is continuous at every point, even though it's not uniformly convergent everywhere? If that makes sense.
I'm not sure I followed that.
So maybe I'll phrase it this way. So if there's a function that isn't a sequence of functions that isn't uniformly convergent on the whole domain, but we can any ball we pick, it is, then can we sort of use this and piece together continuity?
Oh. So, I mean, yeah, I mean, you could piece together continuity at every point. But then, did you really have uniform convergence on the entire ball anyway?
I guess it might not be like a realistic scenario. Uniform convergence might not let that happen. Might cover that case already.
Yeah, I mean, so the answer off the top of my head is yeah, that sounds like that would work and give you something that's slightly stronger than the hypotheses would tend to say. I would agree that you'd want to double check that there actually are sequences of functions that satisfy your hypotheses, but don't converge uniformly. Okay, but if such sequences of functions exist, then what you're outlined there is, proof that their uniform limit would be continuous, which is a nice proof. Okay?
Okay, thank you.
Okay, and Benjamin asked some questions in the chat, which I'll finally get to. He said, could we loosen the assumption, because we don't even need to use the fact that all the fn's are close together, just this f sub capital N. So I agree that's a tempting thought. F sub capital N is the only one we use. We don't use f sub little n. The problem is we don't know what that capital N is going to be. So it's correct that we only use one of the functions in our sequence, but we don't know which one we're going to need to use going in. So we really do need them all to be continuous. And then it seems like you've already thought that through, Benjamin, and yes, your next suggestion in the chat is definitely legit. Okay, so we wouldn't, okay, wait, I take it back. Okay, so first of all, if you have a sequence of functions and a subsequence converges uniformly, then you might as well throw away all the other terms and only keep that subsequence, and then your sequence converges uniformly. Now, however, what you say in the chat makes sense if you think about continuity. If you have a sequence of functions and they all converge uniformly, sorry, this is going to be the same argument. If they all converge uniformly to if the sequence converges uniformly, but only a subsequence is continuous at A, then you still get continuity at A of the limit. But again, we could just throw out the ones that weren't continuous at A.
Okay, that's fair. But it's nice to think of the subsequences, because I thought maybe maybe going off a rabbit trail to think maybe there's some kind of a metric space with functions that's, what do you call it, like, where every sequence of functions has a convergent subsequence or something, but I think I'm going a little too far down the rabbit hole.
Right. Pretty soon we're gonna define the uniform metric, and then our metric space is going to be functions. The functions are the points, and the metric is the uniform metric. And then you take a Cauchy sequence of functions, you got a convergent subsequence. Yeah. We'll get there. We'll get there. Okay. Now I want to emphasize the first and the last questions I dealt with here. They both kind of the standard things we keep talking about, and I want to just remind you that all of these theorems, because they're so abstract, they hold a lot more generally than you might think. Okay? Because first of all, you can always restrict the domain. And so even if you only have this thing in a little tiny neighborhood of a point, you're still good. You just restrict the domain and you get it. And the other thing is, a theorem about a sequence of functions, if it's got a nice subsequence, you can always restrict to that subsequence. Okay? So those are two ways that you can always make these theorems, seem a little bit stronger. Right? You might not literally have the hypotheses, but you can restrict to get the hypotheses. And then that's all you really need to get whatever you want to get out of the theorem. Okay? So there may be, maybe I should say they're just a little bit more applicable than they look. Okay. Good. This is our big theorem today, so if you have any more questions, let's get them out now and make sure we all understand this thing.
So we need the uniform convergence
Oh,
because both of the inequalities in yellow come from the same property.
Yeah. So we need uniform convergence with just pointwise convergence. This is a good thing to check. With just pointwise convergence, we would have issues in these yellow quantities. Because we wouldn't get to use the same subscript there. Okay. Okay. Let's look at a couple consequences of this. So this theorem was just stated about continuity at a point. Well, we can make it continuity on all of x. So this is your corollary. I'll just be short about this. Let's say if every fn is continuous, remember we just call it continuous if it's continuous on the entire domain. And the convergence is uniform, then your uniform limit f is continuous. This version follows immediately from our theorem because just our theorem says it's continuous at every point. So there we go. Now Daniel had that idea that maybe you wouldn't have continuity. Sorry, he said maybe you wouldn't have uniform convergence everywhere, but only in a, restricted to a ball around every point, in which case you could paste it together and still get this. But anyway, this is the immediate corollary. So uniform limit of continuous functions is continuous. Now we saw last time that this isn't true if we just have pointwise limits. So let's go back and look at an example. Okay, now this is a non-example. Let's define, we'll just do the polynomials here. Okay, then Fn converges pointwise. To this guy. Okay. Again, let me repeat. I said this a lot last lecture, but The pointwise limit is frequently just something you can look at and just see. So in this case, let's say this came up on a homework or a quiz and you have to state the pointwise limit of this sequence of functions. There's really nothing to prove. I mean, you know, underneath this, there is some things to prove. You're proving that x to the n goes to 0 if, you know, so fine, there's some things to prove there, but we wouldn't prove those things now. Those would be things we proved in the first month or two of the last semester. Okay. So now, you know, this statement that it converges pointwise to this function is just kind of a thing we state. Okay. Now I bring up this example first to show that we need the uniform convergence hypothesis, but also now we see that this convergence can't be uniform. Okay. And let me just point out that, like, if last lecture we had seen a sequence of functions and we had said, prove that the convergence isn't uniform. That would be a little bit of a pain, I think. Right, what would you have to do? For every epsilon, you'd have to find a point and a point. For every epsilon, you have to prove that no capital N works. So for every capital N, you'd have to find a point, et cetera, et cetera. I think it's a lot easier just to say, well, if the convergence were uniform, then our limit would have to be continuous, and look, it's not. Okay? Any questions there? Okay, let's do one more theorem, one more consequence of uniform convergence. This one I don't think we actually remarked on it last semester. First, we need a definition. Let's do two definitions. So first, can anyone remember the definition of a bounded set in a general metric space? Uh-huh. So the set S is bounded if, okay, so we need to have a point and a radius. Okay. So that's a review definition. We've already seen that. And now what does it mean for a function to be bounded? Any volunteers here?
We'd say the image of the domain is bounded in the codomain.
Yeah, yeah, just the range is a bounded set in Y. So what do we want to, I mean, I guess if we write it out, that would mean, so here, if and only if f of x is bounded in Y, and if we want to write it out, this would be if and only if there is a point in Y in a radius such that our range is contained in that ball. Okay. Any questions? Here's our second and final result of the day, if you don't count corollaries. The short version is just the uniform limit of bounded functions is bounded. And now to state that, we just need to do our things here. We need two metric spaces. So they're all bounded, and then the sequence Fn converges uniformly to F then F is bounded. Okay. X still Y's metric? Oh. Nah, it's just bad handwriting. Okay. So this result, I will leave it to you to construct an example. This does not hold for point Y as convergence. You need the uniform convergence here too. Okay, any thoughts about how to prove it?
You have, since all the FNs are bounded, the Fs are going to be some distance close to them.
Uh-huh.
So you're close to something bounded, which will make you bounded.
Right. Yep, you're close to something bounded, which will make you bounded. That is morally the proof. And now we have to think, so there's a triangle inequality in there. That's when you're close to something that's close to something else, you're close to it. And then there's one more trick in here, which we've used a bunch. How close do we want our functions to get to f? So kind of what epsilon do we want to take?
Probably epsilon over 2 or 3.
No, this is the other trick.
But doesn't epsilon have to be arbitrary though?
No, see, the thing we're trying to prove doesn't have an epsilon in it.
We want
The radius.
I mean, that would work. Okay, but what radius are you talking about? The radius of which function? F1, F2, F3?
Of capital N, right?
Okay, but what's capital N then?
For the limit of functions such that, for the pointwise limit. That you're.
No.
Just N in uniform convention.
So every single Fn is bounded. If F is close to any of the Fn's, then it will be bounded. Okay? By the triangle inequality. Now, how close do we want it to get to one of the Fn's? Why don't I write down, okay, here's what we're going to start out with. Because the sequence Fn converges uniformly to F, there is some capital N so that the distance in y between f of x and f sub n of x is less than, this is what I'm asking you for, what's the epsilon we want to put in there? Whenever we have, who said 1?
That was me.
Yes, good, Zach. That's what we want to do here. This is a trick that we have done quite a few times. We don't really care about that number. Any number would work there. But don't try and overthink it. Like you guys were trying to overthink what you should put there. Like, should we put the radius or, blah, blah, blah. No, just put a number there. Okay. And then, now this goes back to like last proof, what we did. This is true for all those little n's, but we don't even care. So now we just say it's true for capital N, and that's all we care about. So in particular, for every x in x, the distance between fx and f sub capital N of x is less than 1. That's all we really care about. Okay. And now, at the very beginning of the proof, Daniel gave us the outline, and that is just what we have to follow now. We're close to f sub capital N, so now we just have to triangle inequality to get our ball. So we should mention that f sub capital N is bounded. So since f sub capital N is bounded, there is a point. And a radius. Okay. Now, okay, what we wrote before would be that our range is in this ball. Okay, that's how we wrote it before. Okay, but I think it's going to be easier if we're going to really write out the triangle inequality. It's going to be easier to do this on a point-by-point basis. So really the distance in y between f sub capital N of little x and y is less than r for all little x. And now we can triangle inequality of this thing. Okay, so therefore for all x in our domain, the distance between f of x and y will keep the same center. So less than or equal to the distance from f of x to fn of x plus the distance from fn of x to to y which is less than r plus 1. Okay, now we just have to write the conclusion, thus f of capital X is contained in the ball for radius r plus 1, centered at y, proving the theorem. In the proof of the first theorem today, a lot of you kind of had this reaction like, wow, we're not really using much of the uniform continuity. Here it's even worse, I think. Right, we're only using this one f sub capital N, and we only picked that just because we didn't even need to get f arbitrarily close to this guy. Okay. But yet, this theorem is not true if you replace uniform convergence with pointwise convergence. Okay, so even though it seems like we're not using all of our uniform convergence hypothesis, we really do need it in there. Okay, well that's the end of this lecture. And are there any quick questions?
Yes, so the reason we need the uniform convergence is so we can get all of the same n's and thus all of the same r's.
Yes. Yeah.
Okay.
Mhm. But, okay, so in case I don't remember to, you might want to think about this theorem once we get into the uniform metric, which will be, should be Wednesday or Friday. And there, this kind of argument has a slightly different implication there when we're dealing with the uniform metric. Okay? Yes. Benjamin points out if it wasn't uniform convergence, yeah. For each individual point x, we'd have to worry about which f sub n we were close to, and then each f sub n could have a different radii, and the radii could be going off to infinity or something, you know, there could be problems. You know. Indeed, indeed, there's actually a pretty easy counterexample to this theorem if you just do pointwise convergence, okay? And I hope you've all seen it. When you do like Taylor series approximations to sine, right? You do like the degree 3, the degree 4, degree 5, etc. Those are all unbounded functions because they're polynomials, okay? But the pointwise limit is the function sine, okay? And sine is a bounded function. Okay, so this tells you that that can't be uniform convergence going on. Okay. Okay. That is it for this section, and I will see you all on Wednesday.